Alright, we're going to do a little quick video. Since I missed some of you people this week, I'm going to try my best to kind of give you some of the highlights of the properties of ionic and covalent compounds. I know period 7, you missed a lot. I think this video will help kind of bring things together a little bit, and then on Monday I think everything will really make sense. You guys will be more than prepared for Tuesday. But what I want to start off with right now is we know that ionic compounds are made of a metal and non-metal. And they form a crystalline solid, which means they have a very fixed rigid pattern. They form through the process of a transfer of a valence electron from a positive cation to a negative anion. And as a result, you see this rigid structure. And I draw it this way, very simplistic. And you notice here it looks like Legos. And I use that analogy that they require a lot of energy to pull them apart. Not to go through a chemical reaction, where I break the chemical bond itself to form something else. I'm saying move apart each molecule individually into a different state, whether it be a liquid or a gas. So therefore, in here in blue, I have what these things are called, these strong electrostatic, well, maybe I should make that blue, that would make more sense, electrostatic forces. Therefore, because of these attractions, and you notice it's lined up to the point where the negative anion is attracted to the positive cation over here. So it's going to take a significant amount of heat to enter this system to reduce these attractions. So we add the energy, and what will happen is as we add more heat and 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 more heat, what happens is these electrostatic forces decrease because we're adding energy to the system. Eventually they would separate and form a liquid or a gas. Okay? But it takes a lot of heat to do that. And we talked about that. It takes a lot of energy, therefore they have a higher boiling point. Okay? So they have a very strong, fixed, rigid pattern. We talked about the Lego analogy in class. Alright, now, so that's the first part. We'll talk a little more in class. The second part is going to be dissociation and dissolving in water. So right here, in fact, I'm just going to do a new drawing. I like to talk as I draw. So here's a beaker right here. Let's take a look. Let's just keep this very simplistic, and then I'll use the FET. So now, inside here I've got water. And we know that water is a polar molecule. It's a covalent compound where we have the formula is H2O. Oh, hello. It's made of 2 hydrogens to 1 oxygen. So we know that oxygen has 6 valence electrons. It's going to form 2 covalent bonds to fulfill the octet rule because hydrogen needs 2 valence electrons in its outer shell and oxygen needs 8. So the way we set that up is this. H, on an angle, it's a covalent bond, like that. Now, there are excess valence here. So this is the negative end of water. Over here, there is no excess valence. These are the positive ends of water. So therefore, water is polar. So polar water, which is known as a universal solvent, this stuff dissolves a lot of different things. It can dissolve ionic compounds, it can dissolve polar covalent compounds, it can dissolve a little bit, some of the non-polar compounds, but not many, but they can also dissolve acids. But let's take, for instance, the most simplistic ionic compound. Let's go back to 1 compound of sugar. I'm sorry, salt, excuse me, NaCl, sodium chloride. So salt comes in, salt's sitting above the water, and there's a gazillion of these in here, okay? And what happens is, this salt, when we drop it in, this is not realistic, but 1 compound of salt, just 1. I'm not talking 10 to the 24th, 1 comes in here. The important thing is that when it comes in, it sees, this sodium says, ooh, negative end of the water molecule. This chloride ion sees, oh, positive end of the water molecule. New attractions form. But in order to effectively dissolve, this actually goes through a process of dissociation. Dissociation, where if it goes in here, as it goes in, what happens? The sodium chloride splits apart, but not as sodium atom and chlorine atom, you would have an explosion. Why would they want to split apart and go back to the way they were? Because this has a full outer shell, this has a full outer shell. They go in as ions, individual ions. Like that, okay? So now this drops in and they dissociate. So what happens is the water then contorts itself and sees these charged small, very small ionic particles and surrounds them. So now I'm going to go to the next screen. We're going to take a look at how it would look. So if I have water here inside the beaker, whoops. Here's the negative end, here's the positive end. Here's the Na, positive. This will develop a little bit of a force of attraction right there. Now watch this. How would I get the next water molecule to arrange? The next water molecule would contort itself like this, because that's the negative end. What would happen over here? That's a negative, so I'm trying my best to draw this. Look. That's a negative sign. Excess valence, positive, positive. I'm trying my best. Again, surrounds the positive kind. This is in the beaker. And again, these little forces of attraction surrounds it. Now, one more. So what you notice, my question is this. We have a sodium ion. Did any of the water molecules break apart to form something else? No, all I have is sodium ions dissolved and surrounded in water. So the solute, small little solute, gets dissolved by the water inside this beaker. Looks like that. But what happens to the chloride ions? So that's what happens in there. But let's take a look at the chloride ion. Here's chloride. Like that, that's negative. How will it contort itself? Watch this. Positive, positive, negative. See where it's at right here? There's an attraction right there. Here's another one. Ah! Again, the negative anion attracts to the positive end of the water molecule, and it will surround it. So this is ultimately a physical change. I didn't make anything brand new. Okay? So on a very small scale, dissociation occurs. Now I've got here free ions floating in solution. And that'll now set up our next property, which I'll show you now on the FET. I'm hoping this is helpful. Now watch this. Let me make sure this comes in clearly, because I've never done a FET on a video before. I think I'm doing my best. Well, I hope you can see that somewhat well. Okay. So now, if we reset everything, oops, please work, please work, please work. You don't, oh, here we go, okay. So now I'm going to put in salt, an ionic compound. There goes the salt. Now, put the conductivity tester in. Keep in mind, on a molecular level, let's go, okay. Reset, reset, reset. Come on, you junk. Okay. Sodium chloride, the ionic compound, there's the crystal lattice structure. Once they enter the water, they split. And they do this right here. And what happens is, now I've got free ions floating in solution. If I drop that conductivity tester in here, boom, electricity. Because you've got free ions floating in solution. Now, keep in mind, as I remove the water in this solution, the light would actually get brighter because the concentration of dissolved solute salt increases because you're decreasing the amount of water. It's a stronger solution. But let me ask you this. If I removed all the water, whoa, look what's happening. We're running out of water molecules to surround the salt ions. What are some of these NaCl's doing? They have nobody else to attract to except what? Themselves. So when I remove this, and remove this, and remove this, and remove this, yeah, a couple of water molecules are left to interact with the other ions, but look what happens. These are left by themselves, they come back together. So take a look. And as a result, you start to see the reconfiguration of that crystal lattice structure. Again, evaporate, 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 boom, there it goes. So now we go back to an ionic compound. If I stuck the conductivity tester in there, you wouldn't get any electricity because ionic solids do not conduct heat and electricity. They must be dissolved through dissociation in solution. So if I took that conductivity tester, remember I put salt in here if you remember, evaporate the water. Whoop, here. Hopefully you can see this. It's getting brighter and brighter and brighter because the concentration of dissolved solute is increasing because there's less solvent. Brighter, 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 brighter. Now picture, hold on. You should start to notice now in your mind that some of the water is leaving. All we have left is solid salt. Done. Solid salt. Solid structure, no conductivity. So ionic compounds do not conduct electricity only when dissolved in solution through dissociation. Now if I were to take sugar, which is a covalent compound, and in this case we'll use sucrose, and if you notice with sucrose, it's made of 2 or more nonmetals, C12H22O11. Shake that into the beaker. Each one of these is each sucrose is C12H22O11. They're clumped together, but when they dissolve, they stay as their molecule. They stay as C12H22O11. They don't actually pull apart. Okay? So if I were to, so they dissolve because they're polar, but they don't dissociate. So if I added sugar to this substance, this solution, no conductivity of electricity at all. Because covalent compounds do not conduct regardless when they're dissolved, except for acids, which we'll talk about next month. Okay, so again, that covers the conductivity portion of the properties. Let's go to an even smaller microscopic level. Where we have, let's reset this again. Right now I've got water, and I'm going to show the partial charges, the negative end of the oxygen, and it goes back to, and I'll draw you again with my disgusting drawing, look at this, the negative end of the water molecule with the positive end of the water molecule, the polar covalent bonds that we have here. How do they interact when through dissociation? Okay, I'm going to take this crystal lattice structure right here, NaCl and ACl. Notice how they're arranged. Pop them in, boom, dissociation. Water molecules surround and contort themselves appropriately around the positively charged cation of sodium here and chloride over here. Conduction can occur because we have free ions floating in solution. So ionic compounds do dissociate in water. Now, take the sugar molecule. Notice this. This is 2 sucrose molecules, C12H22O11. Again, covalent compound, 2 or more nonmetals. Put them apart. They stay who they are, but they're polar, so they do have some sort of interaction with the water molecules. And we'll still get the structures after break. But again, they dissolve, but they stay together. They don't dissociate. Okay? And as a result, they don't conduct heat and electricity. Alright? So again, with dissolving, it's going to be the big theme throughout the rest of the year in this course, even into biochemistry. You're going to need to understand that polar molecules dissolve in polar substances. Polar likes polar. Polar dissolves in polar. Non-polar substances dissolve non-polar things. So we always say like dissolves like. So I always say, well, how do you wash your hands? Well, oil and grease is non-polar. Okay? Soap is non-polar. You're eventually going to learn how we call micelles, M-I-C-E-L-L-E-S. How do they form? They surround dirt. And what happens? How does the dirt get off your hands? The kinetic energy of the polar water doesn't interact. It pushes them off your hands. We're going to do all of that. The chemistry of water, the chemistry of soap. But you need to understand, why does an oil and water mix? Why, if I shake up water and oil, why do I see these bubble-looking things? Actually, what happens is they form these, like, hydrophobic barriers. Hydro, notice I use the word hydro, prefix hydro, water, phobic, fearing. Oil doesn't like water because they're non-polar. So they form these barriers. They don't want to be in there. That's why they separate. Okay? So we're going to learn all about that. In fact, when we get back from break again, we have our first lab of the year where we're going to be looking at M&Ms. We're going to use 3 different M&Ms, 3 of the same color. We're going to put the one M&M, which is coated with sugar. We're going to put one of the M&Ms in something called mineral oil. Then we're going to put another M&M, same color, in water. And then we're going to put the other M&M in rubbing alcohol. And we're going to take a look and see what happens and use the concept of dissolving in polarity as the foundation of what we're going to be learning in that lab. So it's going to be pretty neat, and that'll be our first lab report. Okay, so I hope that got you off to a good start if you missed a lot of class. We'll fill in loose ends in class on Monday. Your test is on Tuesday. You know, we're doing an outstanding job. This is where it really gets fun, and this is where all that hard work is starting to pay off. All right, hopefully you check out this video, and that's it. Write down any questions you have. We'll go a little more in depth on Monday. All right, later.